Okay, so we are discussing quadratic forms, which is section 7.2. Okay, and they have a nice intro here. I'll just read it here. Until now, our attention has focused on linear equations, let's see. I don't necessarily need to say everything, but quadratic forms occur frequently in applications of linear algebra to engineering, in design, criteria, and optimization. I took a whole class on optimization, signal processing, and they can arise in physics as well, economics, statistics. Definitely quadratic forms are important. How many have heard of confidence intervals for a parameter in statistics, a confidence interval? Like, yeah, and Wastina's heard of it, and Ryan has, and so you can have, okay, a lot of people have heard of it. You can have two parameters and have a confidence ellipsoid around the coordinate. The parameters as a coordinate. That is, something that comes up, like for instance in multivariate statistics. So a tremendous amount of applications. So what is a quadratic form, though? Okay, well, a quadratic form is a function Q defined on n-dimensional R space, and the Q of x is equal to x transpose times A times x, and that's going to be a scalar. It turns out x transpose times A times x is a scalar, and the matrix A is called the matrix of quadratic form. So you've already seen a quadratic form. If you take for instance the norm of a matrix of a vector x and square it, that can be written as x transpose x, but that's the same as x transpose times I times x. Okay, that's an example of a quadratic form. And I'm going to take you through some examples here. Okay, in example 1, they say, let's say we have the vector x1, x2, compute x transpose ax for the following matrices. Okay, so you have A and B. You have two matrices here in A and B. What kind of matrices are A and B? Are A and B, or I should say, the A matrices for parts A and B. What kind of matrices are those? Okay, hold on. We got to. They are square. That's right, Binyam. Anything else? Ah, right, Solomon, right, Westina. They are symmetric as well. They are symmetric matrices. So remember here, in the definition of a quadratic form, the matrix A here has to be a symmetric matrix. So we only do quadratic forms for symmetric matrices. Okay, so hold on. Question. Well, that's a very good question, Solomon. I never actually thought about it, but I think when you look at a few examples, and particularly the one I'm going to do a little later on, you'll get a feel for it. It has to do with. I'll tell you why. It has to do with orthogonal diagonalization. Remember, symmetric matrix A, you can orthogonally diagonalize symmetric matrix A. So we want to take advantage of those properties, and they will be used in this particular section. So if A is equal to 4003, okay, notice that the cross elements are zeros. then X transpose A would turn out to be 4x1 squared plus 3x2 squared. Okay? Now, for B, the matrix A is 3, -2, -2, 7. And if you work out the quadratic form there, and really it's just a matter of doing the matrix multiplication. In the end, you're going to get 3x1 squared minus 4x1x2 plus 7x2 squared. Okay, and they comment that the -4x1x2, which is a cross product term, you didn't see a cross product term in A, but you see it in B. And the reason you have that is because of the -2's off the diagonal in that matrix A in part B. That produces a cross product term. Okay, that's a cross product term. Are there any questions on example 1? Okay, which quadratic form is more simple for an example 1? The one in A or the one in B? Which is more simple? That's right, A, because you don't have those cross product terms. Okay. Well, let us proceed on here. And I was going to mention, class, the example they mentioned about confidence ellipsoids. I'm going to review that a little bit because it's been a while since I've seen that. I want to make sure I'm, saying it right. But it's a statistics application. So I think the next class I'll try to talk about that a little bit more. All right, let us continue. Let us continue. In example 2, here they give a quadratic form, and they want you to write the quadratic form as X transpose times A times X. So you know that X, the vector X, is going to be X1, X2, X3, but what you have to identify is what's the matrix A? What's the matrix A? Well, here is the matrix A. Okay, I'm just highlighting the values. And gosh, the 5 and the 3 and the 2 along the diagonal, where do those come from? Those are the coefficients of what terms? Are they the coefficients of the cross product terms? So for this X transpose AX in example 2, I've highlighted the matrix A, and the 5, 3, and 2 are coefficients. Look above here at example 2 when they say what Q of X is. The 5, 3, and 2, are those coefficients of cross product terms or coefficients of non-cross product terms? That's right, Rustina, the non-cross product terms. The non-cross product terms. That's right, Robin. Well, now let's see here. We have a -1/2 and a -1/2. Okay, a -1/2 and a -1/2. And notice that the -1/2 in this matrix A is located in the first row, second column, and also in the first column, second row. Okay, so -1/2, -1/2. They're located in the spots in the matrix A. That's it. First row, second column, also first column, second row. Okay, now we want to try. We want to try looking above here, looking here at this matrix Q. Let me just kind of remove some of this. Can the negative half, negative 1/2 be related to any of the numbers up there? Any of the coefficients of the matrix Q? Notice that negative 1/2 plus negative 1/2 equals, that's a hint to you. The negative 1. That's right, Solomon. Notice the negative 1 in front of the cross product x1, x2, the cross product term, I should say. Negative 1 is the coefficient in front of the cross product term x1, x2. And coincidentally, negative 1, if you split it in 2, you get negative 1/2. And in the matrix A, negative 1/2 occurs in the first row, second column, 1, 2, or in the first column, second row. Hold on, 2, 1. But you see x1, x2, 1, 2, 2, 1. Just trying to, let's look at the 4 and the 4. Let's talk about the 4 and the 4. Let me take the halves off. Let's talk about the 4 and the 4. Too much. Hold on. Man, hold on. I just want to get this guy here. Good. The 4 and the 4. All right. Hold on. I'm getting some responses. That's 4 and 4 make 8, and that's the coefficient, right, Robin? Right, Solomon? The coefficient of 8. The 8 is the coefficient of the cross product term x2, x3. Notice that the 4 there is in the second row, third column. Boom. You see? So it's going to work out. It's going to work out, and that's how you create your quadratic form, the matrix A of your quadratic form. Okay. Are there any questions at all? Okay. All right. Well, then let's proceed on. Let's proceed on. In example 3, they have a matrix Q here. I'm sorry, a quadratic form Q. And they want you to compute the value of the quadratic form for these 3 vectors. So Q is a function of the vector that you put in it. So like, for instance, if x were equal to negative 3, 1, okay, the quadratic form will yield 28. Of course, what they're doing is just substituting it in the quadratic form, which incidentally, this quadratic form can be geometrically, in example 3, can be geometrically interpreted as an ellipse. That is not an up and down ellipse, not a cross ellipse, but an ellipse that's askew, at an angle. Okay. And they compute all the cross products, it's quadratic forms. They compute all the values, but they mention here that quadratic forms are easier to use when they have no cross product term. Okay, we already saw that in example 1, right? When the matrix of the quadratic form is a diagonal matrix, then the quadratic form, you're not going to have any cross product terms. And the beauty is we can eliminate the cross product term by making a suitable change of variable. Okay, how many remember calculus 2? When you did like the substitution, you made a change of variable. And in calculus 3 also you did, yeah, well, this is how you make a change of variable in a linear algebra sense. Okay, this is how you do a change of variable. What you do is you say, okay, let x equal p times y, where p is an invertible matrix. If x is equal to p times y, then y would equal p inverse times x. Okay, certainly that's true. Certainly that's true. So if you know the y, if you have this vector x, you can make a change of variable to the vector y by having y equals p inverse times x. Okay, and they note here that y is a coordinate vector of x relative to the basis r determined by the columns of p. Okay, so there were, you remember coordinate vectors from, I believe it was chapter 4, yeah, chapter 4, section 4.4. All right, I mean, that's cool. That's cool. It's right there, section 4.4. So how does this work? Well, look, if you have x transpose times ax, that quadratic form, you can substitute in py for x. Okay, but by the property of transposes, py transpose is y transpose times p transpose. Okay, y transpose times p transpose. And what's going to happen is in the middle you have p transpose times AP. Okay, and that's the new matrix of the quadratic form. But remember, A is symmetric. So that ensures that you're going to have an orthogonal matrix P such that P transpose times A times P is a diagonal matrix D. So therefore, P transpose times A times P will become the diagonal matrix D, and the quadratic form becomes this new quadratic form, which is y transpose times D times y. Okay, that's what that means. Okay, now let me just write down one thing here, one moment. Are there any questions so far before we go to example 4? And all right, let me bring something to your attention here. Let me go on the whiteboard. So what you're used to seeing from section 7.1 is if A is symmetric, only if A is symmetric, then A equals P times D times P transpose. Okay, but if you multiply P transpose times A, left multiply then both sides of this matrix equation by P transpose. And remember, we're assuming A is symmetric. Okay. Let me see here. One moment, class. I'm just right. So what's P transpose times P going to equal? Well, what kind of matrix is P? When you have orthogonal diagonalization of a symmetric matrix A, what kind of matrix is P? Has a special name. Give you a hint. Orthogonal. Good. Good. Well, Matthew was first, but you were all quick on the draw. You're all right. Okay. Maybe Matthew will have to enter that Jeopardy show once they get the new host and everything. Okay. So what is then P transpose? Okay, no problem, Matthew. What is P transpose times P equal to? Since P is, it's the identity. And so now you have P transpose times A equals D times P transpose. But what I'm going to do now is I'm going to multiply the right side of the matrix equation by P. Okay, I'm going to write it by P. Multiply on the right side by P. P transpose times P is the identity. And so what you get is that the diagonal matrix is equal to P transpose times A times P. So what you're used to seeing from section 7.1 is A equals P times D times P transpose, right? We did a problem like that in our class last week, last Thursday. We worked through a problem where we orthogonally diagonalized a symmetric matrix A. The matrix P consists of the eigenvectors, but normalized so that they're length 1. And also you have to be sure that your eigenvectors are all orthogonal. And if you have a couple that are in an eigenspace that aren't, you have to use Gram-Schmidt to orthogonalize them. But given this is true, and you can find a matrix P that will work and a matrix D that will work because all symmetric matrices are orthogonalizably diagonalizable. Given this, A equals P times D times P transpose, then the diagonal matrix D is equal to P transpose times A times P. And the reason I'm mentioning this is because when in that discussion on the change of variables, they make use of that fact. They make use of that. Okay, so that being said, I'll go back to the book unless are there any questions? Okay. All right, all right. Well, then let's go back to the book here. Let's see, back to the book. Yeah, so here when they talk about change of variable in the quadratic form, when they say here that P transpose times A times P is a diagonal matrix D. Now you know why that. Now you know that to be true. And basically, what that change of variable does is you can take a quadratic form that has cross-product terms and convert it into a quadratic form that has no cross-product terms. So like here, in example 4, they say, all right, make a change of variable that transforms the quadratic form in example 3 into a quadratic form with no cross-product term. Okay, so, whoops, hold on, I went too far. Hold on. So here's example 3. The matrix A, okay, the diagonal, that quadratic form has a cross-product term of negative 8x1, x2. So along the diagonal, the matrix A, we know we're going to have a 1 and a negative 5. And then opposite the diagonal, opposite sides, you're going to have a negative 4 and a negative 4, right? So this is your matrix A. And you can orthogonally diagonalize the matrix A. You're going to get two eigenvalues, two eigenvectors. You know how to get eigenvalues and eigenvectors. And then, by the way, are these two, are the eigenvectors for these two eigenvalues automatically orthogonal? I mean, would the eigenvectors for in different, if you have an eigenvector, if you have a symmetric matrix and you have an eigenvector in one eigenspace, will it automatically be orthogonal to an eigenvector in a different eigenspace? The answer is yes. Good, Robin. Good, Solomon. Yes, and that's one of the we actually saw that in the last class. Okay, so you construct the matrix P, you construct the matrix D, that's orthogonal diagonalization. And then you define X to be equal to P times Y, where X is your X1, X2, and Y is Y1, Y2. Okay, well, then once you do that, okay, are there any questions so far? All right, I'll keep moving then. The quadratic form using the defining X to be equal to P times Y, the quadratic form x1 squared minus 8x1 x2 minus 5x squared, it turns out will equal y transpose times d times y, and that's 3y squared minus 7y2 squared. Okay. Okay, so like for instance, if you wanted if you go back to the previous example 3, they compute, let me just take this off, for the vector 2, negative 2, they compute the value of the quadratic form, it's 16. But of course, it took a little bit of work to get that, right? And it isn't a big deal for a 2 by 2, but what if you had a 3 by 3 or a 4 by 4 matrix, or even larger? You know, what if 100 by 100? You're going to have a lot of cross-product terms, right? So by using this change of variable, we can break the quadratic form down into a quadratic form that doesn't have any cross-product terms. And so by making the change of variable, the quadratic form evaluated at for the vector negative 2, 2 is, well, they show it here. It's going to equal 16 again, as it should. But the vector y, of course, the 2 and -2, that's vector x. The vector y would be 6 root 5, -2 root 5. But look how much easier it is to compute the quadratic form. You don't have any cross product terms. How many think that's kind of cool? Okay, Christy's kind of cool with it. James is cool with it. Yeah, I mean, imagine if you had a 100 by 100 matrix and you had to compute a quadratic form. Look how much computer time you'd save. Thank you, Sega. Sega likes it. All right, all right. Well, that being said, they have just a little graph here that shows you, you know, how two quadratic forms, one that's complicated, one that's easier, could give you the same result. And we basically saw that. And, you know, they both give you 16. This illustrates what's called the principal axis theorem. Principal axis theorem. If you have a symmetric matrix and you do this orthogonal change of variable, okay, it's going to transform the quadratic form x transpose ax into a new quadratic form y transpose dy that has no cross product terms. Okay, are there any questions on that? All right, need just a little more time here to, let's take a little more time. So we'll talk a little bit more about the principal axes. We'll look at an example. They give some ellipses and so forth, some graphs. We'll take a look at that the last part of our class. Here they talk about classifying quadratic forms. Okay, so quadratic forms can be classified three ways. You can have a positive definite quadratic form, and that's if the value of a quadratic form is always positive for x when x is not equal to the 0 vector. Okay. Negative definite if the value of the quadratic form is always negative. And then indefinite if the quadratic form assumes both positive and negative values. Okay, and they have some quadratic forms here. They have some quadratic forms. Let me ask you A. In A, is the quadratic form positive definite or negative definite? We know that z equals 3x1 squared plus 7x2 squared is a quadratic form. The matrix A is would be 3, 0 on the first row and 0, 7 on the second row. That would be, let me see here. Hold on. That's right, positive definite. That's right, Christy. That's right, Wastina, positive definite. What about D? What about D? In the figure 4 above, D would be negative definite. Okay, good, Wastina, good, Solman. Because again, that z equals negative 3x1 minus 7x2 squared. That right-hand side is a quadratic form. It can be written, you know, as, well, you know, x transpose times a times x, where the matrix A would be, what, negative 3, 0 on the first row and 0, negative 7 on the second row. What about C? What about C? Good, indefinite, indefinite. Okay, very good, very good. So these are terms that you will hear. How many maybe have heard these terms kind of maybe in other classes, you know, positive definite, negative definite. Okay, Noah's heard of it. Okay, and you know, for the second derivative test. Okay, okay, okay. Well, you know, I'm teaching multivariable calculus next semester, Math 280, along with differential equations. So maybe you know, I'll be looking forward to seeing that. All right. Well, that being said, they also talk about positive semi-definite. If your quadratic form is greater than or equal to 0 for all x, so it could be allowed to be equal to 0. And negative semi-definite, if q of x is less than or equal to 0. Okay. Now, another theorem here. So if you have a symmetric matrix, the quadratic form is positive definite if and only if the eigenvalues of A are all positive. Okay. A quadratic form would be negative definite if and only if the eigenvalues of A are all negative. And finally, C, quadratic form is indefinite if A has positive and negative eigenvalues. And that really honestly makes sense based on the pictures above. If hold on now, let me make sure. Yeah, the pictures above, well, I want to be a little bit careful here. I'm going to be a little bit careful, but let me show you one thing here. In example 4, you had eigenvalues 3 and negative 7, right? 3 and negative 7 for example 4. And when you made the change of variable, the equation for the quadratic form became 3y1 squared minus 7y2 squared. So the coefficients are in, when you do this change of variable, the coefficients of your quadratic form are the what? The coefficients of your, when you make the change of variable, coefficients of your quadratic form are your what of A? They are your well, here are your eigenvalues. Your eigenvalues were 3 and negative 7, right? And after making the change of variable, look at your coefficients of y1 and y2. 3 and negative 7. So the coefficients, that's right, Solomon, are the eigenvalues. I mean, absolutely amazing how important the eigenvalues are. Okay. Are there any questions on that? Christy agrees. Any questions? Well, Solomon, I understand what you're saying. I do understand what you're saying. Yes, there is a correspondence. Very good. Well, on that note, let me stop the recording.